So, good afternoon, everyone. Today we have one more eminent speaker from IIT Bombay, Dr. Sandipkumar Saha, sir, who is currently working as an associate professor of mechanical engineering department at IIT Bombay. Sir received his BE degree in mechanical engineering from Jadavpur University, Kolkata, and then MSc and PhD degree from IISc Bangalore. Prior to joining IIT Bombay, he was with R&D Tata Steel India as a researcher and applied mechanics and energy conversion. Department of Mechanical Engineering, Catholic University of Leuven in Belgium as a postdoctoral fellow. He has received BASc fellowship to conduct research on solar thermal applications in USA. His research interests include computational fluid dynamics, heat transfer, thermal management of electronics, microchannel cooling, thermal storage system for solar thermal application, and thermal management of building. Sir has published a number of research papers in reputed journal and conferences, and filed almost 6 patents on his credit. So with a great biodata, sir, I would like to thank you on behalf of AD Patel Institute of Technology. Over to you, sir.
Thank you, Professor Said. Thank you for inviting me for this lecture. I hope it will be a wonderful lecture. And if you have any questions, please let me know after the presentation. I hope it is visible to you.
Yes, sir.
Thank you. So my talk is on applied computational fluid dynamics for renewable energy systems. Here today I will give a brief overview on the energy systems, especially for solar thermal applications. I mainly work on solar thermal applications. Also I work on geothermal applications. But today I will give presentation on solar thermal applications. So here I will demonstrate that how the computational fluid dynamics is used to analyze the performance of the system as well as design of the system. And you know that if I use some computational methods, that means I need to validate that model. Okay, so I will show some validation part. So mainly I will give you brief overview on the different types of modeling approaches we adopt to analyze the energy systems. Here today I will tell you specially the thermal energy systems. Okay, so I am not going into like collectors or receiver type of systems. Rather, I will concentrate on solar thermal storage systems here today. Very specific now. And I will demonstrate again that what are the techniques are available to analyze these systems. So first, why we need solar energy? So obviously this is renewable, and in most part of the world this energy is abundant, and also it is environment friendly. And at the present day the operating cost for solar PV is very low, as the material science research has improved a lot. Also this the solar energy could be a solution for home or cluster of villages, or even small villages also. And it could be a solution for the power needs for off-grid systems basically, or off-grid electricity requirement systems basically. So normally means if we talk about any systems which actually generates electricity, we are thinking to put into the national grid, which actually means then it will be very useful. But solar energy is very much useful if you use it for a decentralized type of applications. What I mean here, So it is, you can also use for large scale electricity generation, something like 1 megawatt to 5 megawatt power plant. And in basically in 1931, that time solar, the New York Times said that the use of solar energy is near a solution. So today we will see that what is the problem with solar energy, and then we will try to develop some technique or some mechanism to handle those problems or to solve those problems basically. So what is our Indian scenario here right now? So the report published by MNRE in 2019-20 shows that thermal energy or source of thermal energy is very high. It is something like 63% till now. So thermal energy means basically we are using fossil fuels to generate that thermal energy. Okay. Whereas the share of renewable energy is only 23% and hydropower energy is 12% and nuclear energy is very small, 2%. Now the target here, something like in 2022, is that India will be increasing that share of renewable energy from 23% to 34%, whereas we are trying to reduce the thermal energies basically, or dependency on the fossil fuels to reduce this carbon emission. So our target is very big, and also we want to produce something like 175 gigawatt by that time. So as in India, actually solar energy is widely available, even and solar intensity is also good. And in a day, you will get the solar energy for long duration, also something like 10 hours, maybe 12 hours also. So our aim is reasonable. So, however, we will see some disadvantage of using solar energy. Okay, so now if we want to produce energy from or electricity from solar, there are two mechanisms you can use. That one is solar PV, another one is solar thermal. So solar PV is almost matured technology, and it depends mainly on the photovoltaic cell.
syllabus UG syllabus UG PG syllabus में discussion में research में हमने नाम જ નથી આવ્યું બોલાવવામાં.
Okay, fine.
Sorry, sir.
Okay. So then, but what about solar thermal? Solar thermal is basically the part where we will basically replace that furnace and the boiler using collector, and the efficiency is something like we can achieve is 18%. Okay. However, the problem with this solar thermal power plant is that if we don't use solar thermal energy storage here, then we will not be improve this efficiency, and it has been calculated that we can improve the efficiency to 22% if we use some sort of thermal energy storage. Now, as you know, what is the thermal energy storage? Basically, what we are doing, we are storing the heat during the, or we are storing the excess heat during daytime, and we will be using that energy where we need it. It could be night, or it could be in the peak hours, basically. For example, in Mumbai, the power demand is something like different. So here our power profile is something like that. During afternoon only, we need actually the high. It's basically a high electricity. Whereas in some places or in most part of the India, there the requirement is during the 6 p.m. to 7 p.m. or 8 p.m. Okay, so that is only the difference. So depending on the peak, basically we can supply that energy using this energy storage. Now here I will mostly talking about thermal storage system, where you will see that using this system, can we actually extend the electricity generation? Simultaneously, we will also try to understand whether we can produce a constant electricity from the turbine. Okay. Now, what is the problem with now solar energy? That this is already known, is that solar energy is intermittent in nature, as well as it is available for very small duration. Now, if I see the DNI profile of the solar energy, then or solar radiation, we will see that in Jaipur mostly where we will get a smooth profile. Wherever in Noida, this is profile for rainy days. Okay, the solar energy or the DNI pattern is very irregular, or it is fluctuating. Okay, that means if I use this solar this DNI without the using of any thermal energy storage, the turbine outlet power will also fluctuate. Okay, and this is not very good for the electrical systems. So that's why we need some type of stabilization to do the thing, basically, or to stabilize this electricity. Now, what kind of thermal energies are available, or why thermal energy first? So there are many energies. Thermals, like you can use the chemical energy, you can use the electrical energy like battery. Then what is the advantage of thermal energy? Because here you are not converting the energy from one form to another. That's why the cycle efficiency will be very much high. Even the cost, if you optimize it, the cost of the energy produced using this say solar PV or solar thermal plus thermal storage will be less than any type of any other type of storage systems. Now, this is a very brief description to give my introduction, that where how this power plant looks like, because when I will start analyzing my system, then you will see that depending on the requirement, I will actually model my system, and then I will analyze the system. Okay, so it is not like that I can just present the CFD model for a particular system, but while presenting a CFD model, I have to understand that what process is going on as a whole, so that I can impose the boundary condition and initial condition on that model and try to get the performance. Okay, so here, as I told you, my objective will be to use some type of thermal energy storage, so to levelize this, to levelize or to reduce the fluctuation, or to extend the electricity generation. Okay, now there are various kinds of thermal energy storage. One is sensible heat storage, and the second one is latent heat storage, and third one is chemical energy storage. So it's basically not a battery. Here we will be talking about thermochemical storage, which is different from battery. So here basically we will be using actually chemical reaction to store energy, and I will show you that how we can model that using our CFD approach. So starting with the very basic sensible heat, which we know everybody, and we will show you, I will show you some equations, and then I will go to the latent heat storage. Again, you will see some different types of model, but I will put these models in the context of latent heat, okay, for a storage system, but it is equally valid for other type, say, other type of storage system, in the sense that modeling thing, in the sense that this the configuration, whatever I will choose, this is widely applicable in, say, chemical engineering, in civil engineering, even in mechanical engineering also. So modeling approach will be same. Okay, only your boundary conditions and say the application will be different. Only that will be the difference basically. So very simple. What I want to do here now, in the context of solar thermal or renewable energy, as you know, that it's a charging and discharging. Means when I need to store energy, I will call that as a charging. When I want to extract the energy, I will call that process as discharging. That means I will go through a cyclic behavior. So that means my storage has to tackle that situation, as well as I will try to model my system in that way. I will tell you what will be the modeling challenges in this. Okay, first, very simple. It's a two tank, basically initially the people developed two tank storage system, and then people have come to the Thermocline or single tank storage system. And how we will do the modeling, I will gradually come, but let us understand what is going on inside. Then only I will develop my numerical model. Please do not think here one is that I will be using some commercial software and I will just click and then I will get the result. Not like that. I have to understand whatever the results I'm getting from that system is giving me, or from that software is giving me the correct solution or not. That means I need to understand a little bit on the fluid flow and heat transfer, basically. So if I see in the, especially I will not talk about two tank system, it is very simple. Whereas in single tank system, if you see, basically it depends on the buoyancy effect. Okay, so hot fluid will be at the top and cold fluid will be at the bottom, and because of that, because there will be no actually convection mostly, because so there will be a thermal stratification, and we want to analyze that system. So now see, mostly we will be handling this phenomena, or will be actually model this phenomena using some natural convection, because although flow is there at the top, we will see, or we see that the basically the Grasshopp's number by Reynolds number square will be greater than 1, where force convection will not be dominant factor. So mostly it will be based on the natural convection approach. So basically we will be taking care using through some density difference. That means I have to incorporate this physics in my computational model. So basically here I will show you some modeling approach, some equations, and then I will try to give you a glimpse that what equation does what, and if you want to fit different physics, what you have to do here in the equations. So again, it's a little bit classification. What is direct storage or indirect storage, and one will be with phase change, another will be without phase change. Here, phase change means I will only tackle, I will only show you the phase change from solid to liquid, but not liquid to vapor. So, but if you are interested, that I can also little bit discuss on that front. But mostly in our thermal energy storage system, we mostly use solid to liquid, okay, not the liquid to vapor. So vapor in the sense that obviously means when water is under water or some other fluid is going through some phase change, so obviously it is coming from the, means it is changing phase from liquid to solid, which I will not be showing right now, but we have also developed that model. So that is also means you can also employ to analyze some other systems. Okay, here mainly I will concentrate on solid to liquid phase change basically. So first here I will, as I am going through the sensible heat storage, so first is technology is thermocline system basically, where we are relying on the temperature gradient in the storage system and try to analyze that. This is our understanding. Now how I will do this, I will tell you very quickly. So now different types of sensible heat storage system. One is a low temperature storage system which employs water, and there are some high temperature storage system which may not, means you can use pressurized water or maybe some other fluid, something like thermic oil or molten salt. Okay, even if you use molten salt, that is also we call as a phase change material, because this molten salt actually solidify at the room temperature, but it will be in liquid form at high temperature. So that modeling approach I will also show under my phase change based material that modeling approach. Okay, so gradually we will now build. So when you use water in single phase, there is no criticality actually. So only basically you know the Navier-Stokes equation and you know the energy equation, you solve it. So only you have to incorporate some physics, which may be the basically the either natural convection or forced convection. If forced convection is there, then there is nothing to worry about much. But if natural convection is there, then you have to incorporate that density difference term. That is only the thing. So now this some other high temperature storage is oil system, then molten salt system. Again, I am giving you this highlight so that you are distinguished between two models. Otherwise, it is not very easy to distinguish the models. And again, I will run the software. Again, I will run my code, but I need to understand what is going on at the background. So I will tell you that mostly. So different type of storage system. Again, here first I will not consider any phase change. So very basic principle I will do. Now here I will introduce one more type of storage system, or this is widely used. It is used in chemical engineering. It is used in mechanical engineering also. Even some portion in civil where they also do some type of storage, CO2 storage, something like that. Okay, so it's a packed bed storage system. Here, this I will show you how to model this type of storage systems. Okay, now these are the different type of storage system I have for sensible heat material. Why I am showing you? Because depending on the type of storage system, your modeling or your modeling approach will be different, and also the domain selection, whatever the domain you will select for your analysis will be different. For example, if I use packed bed type of storage system, I can use two types of modeling. One is the discrete element modeling, another is the porous medium modeling. Okay, now in discrete element modeling, which is I am not showing, but it is not very much complicated. Why? Because you have to use, or you have to model, or you have to use the heat transfer fluid separately, as you have to use the heat transfer fluid as well as the solid material separately in that model. Only where is the bottleneck? Bottleneck is the computational power, because see, in a thermal energy, in a container, you can have like 1,000 or not 1,000, more than 1,000, is 2,000, 10,000 this type of spherical balls or capsules. Okay, if you want to model individual ones, the challenges are that the first challenge is the meshing challenge. Second challenge is the meshing in the thermal energy storage, where the two spherical balls contacts each other. So there, if you see the contact point if it is a contact point, then you don't have any gap between these two spheres. Okay, then the modeling is very difficult, or meshing is very difficult in those cases. So what people adopt is that they shrink the diameter in those cases and try to model the contact point. Okay, and they try to show that if I shrink the diameter by say 99% or 98%, then how much change in the result will happen. Okay, so this is first technique in any numerical models of this type of storage system. So this is discrete element method. I am not showing here, but again, the formulation, whatever I will show here, it is equally applicable there. But discrete element model is mostly challenged, or it is challenging because you have to distribute the particles randomly before any computational fluid dynamics simulations. Okay, so that type of software or that type of numerical model has to be there, so that numerically you can distribute this particle randomly inside the thermal energy storage, and then you can start analyzing the thing. So there are several challenges in discrete element method. Now, if I go into the next thing, where I just show you that basically packed solid cylinders, means cylinders are packed, or the filler materials or the say sensible heat materials are packed inside this tube, inside this small tube, and the water or whatever the fluid is going outside through in this annular portion. So here the challenge is that how we will select the numerical domain. So normally, if you have multi-tube system, what people used to do is that they take only one section, okay, and then they imagine one circle around. So if it is already drawn, so they imagine one imaginary circle around that sphere or around that tube, where you will assign zero conduction heat flux. Okay, so they are saying that that there is no conduction, or the dt by dx or dt by dy is 0, say, for in the at that interface. Okay, so that if you only simulate or only analyze one tube using those boundary condition, you can replicate the thermal performance of entire system basically. So similar type of approach or same approach you can adopt at the bottom one, where solid material is in the annular section, whereas through tube this heat transfer fluid is flowing. So similarly, if you see the figure B, which is basically packed solid flat, again if you take a simple cross section and or symmetric basically, then you can symmetric means if you take one section which is which you can replicate, or and if you use symmetric boundary conditions at the side walls, then you can represent the whole system analysis. Okay, now what are the different types of storage material? Some properties I have given, because depending on the situation and depending on the application, you have to choose that material. Okay, now sorry. Okay. Oh. Now first model is, this is very simple model. Why I'm telling you, from here I will start developing all of my numerical models. Okay. Now first is I will talk about the sensible heat storage material. Okay, where if you see that here some flow is occurring through this cylinder. Now thing is that if you see this construction, you will feel that it's a flow through a pipe. Okay, it's a flow through a pipe, but it's not like that. Okay, yes, apparently it shows that it's a flow through a pipe, but not. Here the velocity of flow is very low. Okay, and as the velocity of fluid is very low, so our objective here is to actually develop high thermal gradient or high temperature gradient, and so that I can get actually I can store the energy here in that form, because if the flow is very fast, you will not get any much thermal gradient. So your dt by dx, or if you along this line, if you say that z along the height line, if you take that as z, that dt by dz, if it is very small, then the storage will not be very high. Okay, so that means always in thermocline type of system, our always aim is to get dt by dz very high. Okay, now how to model this? Obviously inlet, I will impose this as the inlet. At inlet I will give the velocity inlet or mass flow inlet, and the side walls I can give some convective heat flux. Okay, so some heat loss could be there. Even if you use insulation, some heat loss obviously will be there still. Okay, you will impose that, and if the flow is a little bit higher than the critical value of the critical Reynolds number, then you will employ some turbulent flow, a turbulent model. But one thing I must tell you here, although your Reynolds number may be at around like 400 or 500 based on the inlet diameter, still we employ K-epsilon model in this case, because here our intention is to identify the thermocline profile, okay, or the sharp change in the interface from hot fluid to the cold fluid. Now what happens, it is observed that at that interface all types of fluctuations happen, or all types of turbulence happens. Okay, and because of this we may not get any sharp interface between hot fluid and cold fluid. Okay, and if we don't get very high temperature gradient, again I'm saying we will not be able to improve the thermal capacity of that system. Okay, so that's why although flow will be the laminar, in this case, if I am means my intention is to analyze that how to improve the interface shape, and how this interface is actually destroying the thermocline profile inside this thermal energy storage, I need to employ some type of turbulence model so that I can understand what is the fluctuation is going on at the interface level. So here, although I will be employing 2D axisymmetric model, but the flow rate is around, Reynolds number will be around 100, still I will employ K-epsilon model to check that. Okay, because in bulk of the fluid will be laminar. Only my intention is near to near the interface. That's why. Okay, now the equations are as usual, but here if you see, it is means in pi flow you don't employ this term. Okay, let me convert to leisure. Yeah, so I don't employ this term. Okay, where rho GB TF minus TI. This is basically taking care of my taking care of the natural convection. Rather here I am saying my convection flow, or the flow is not actually the forced convection or the natural convection. Rather, my flow is mixed convection, we used to say. And if it is mixed convection, that means I have to put this expression or include this expression in my numerical model, as well as I have to give fluid velocity inlet at the inlet basically of the thermal energy storage. Okay, so here the modeling approach, whatever I adopt, please see that I have used this buoyancy term. So to understand that what will happen if there is a change in the buoyancy. Okay, now obviously here I am using some K epsilon model in say in commercial software such as in Fluent or Console. These values, these constant values are given because they have set these values for a wide range of application. Although let me tell you that we can employ model. Okay, now whether that model is working or not, that we have to validate first. Okay, I can employ any type of model. Okay, like K epsilon, K omega, any turbulent model, even laminar flow also I can employ. So my next intention should be, okay, it is already done. Now how I can actually validate my model, like whether K epsilon model is justified or not. Okay, so next thing is the validation of my model always. Because same model you will be using for different situations. So now you have to always check K epsilon model is good or K omega model is good, or maybe Reynolds stress model is good. So that how you will get that only you can, if you do some experiments or if you get some experimental results, then only you can compare your result. So here what we see that means there, even if we use laminar, although flow is laminar, if I use just laminar flow model, my error with this temperature profile is basically the outlet temperature of the heat transfer fluid from the storage basically. Okay, so I am comparing that. Okay, even I can compare the inside temperature profile. Here I have just showing you one case. Okay, so where I am seeing that if I use K epsilon model, it is giving me more accurate result compared to other types of model basically. So here I am saying that as a low RD K epsilon model basically. So this is first modeling approach I have adopted. Now I am going quickly into the phase change model, where I will be only looking into the solid to liquid phase change basically. Now if I go from liquid to vapor, the modeling approach is different, technique is different, so which I am not covered here, but if you want I can briefly describe that also at last. Okay, now first take us some phase change material like paraffin. If you heat it, okay, it changes phase from solid to liquid. Now question is how I can model this, and you will see that now that means the level of modeling approach or modeling will be complicated. Although in all commercial software different types of models are available, still the framework you have to understand so that you can decode the results whatever you are getting at last. Okay, now why it is advantage? Because the second law efficiency is higher because of the addition of the latent heat basically. Okay, now what is the procedure to select this? There are several procedures you can adopt. There are several criteria. First criteria is that it has to be the application, the melting temperature has to be same as the application temperature or slightly below the application temperature, and high latent heat. This you will see in the governing equation itself. Now different types of phase change materials are available, like molten salt, okay, which changes phase from solid to liquid. There could be some type of material which can change phase from solid to solid. Only while changing the phase from solid to solid, they only change the structure, crystalline to amorphous structure. Okay, now how to model that? Here I will give you some glimpse. Okay, now but I will be mostly discussing that solid to liquid phase change basically. So some examples depending on the melting latent heat of fusion, and you can choose different types of phase change material. Now this is very much important. Why? Depending on the structure, you will now choose the numerical model. Now I have intentionally showed three structure here. One is here, which one is called the shell and tube heat exchanger, where a heat transfer fluid is flowing through the tubes and phase change material or some material is kept in the annular section, which I told in solid in a sensible heat storage. So remember, the modeling approach for sensible heat storage and PCM will be means more or less same. Okay, but if you switch on certain parameters, you will see you can replicate the sensible heat storage material. Okay, that means if you are modeling phase change based material, or if you are developing models for phase change based material, you can easily simulate sensible heat material. That's why I'm not giving stress on sensible heat material. I will be giving more stress on this modeling. Okay. Now, second part, as I told you, it's a packed bed system, which I didn't show you. Any model I haven't shown you till now, which I will show under this example. Okay. Now, depending on the structure, I will now choose my numerical model. So now, if I see this first one, this one I call it shell and tube heat exchanger. Right hand side, two more geometry I will call the this packed bed type of storage system, where this filler material, as I told you, I can model using one discrete element model. I can also model it using porous medium model. Okay, I will gradually come into details of those two models. Let me first describe the shell and tube model first, which is simple. So it's a one step ahead of sensible heat material equation, what I told you. Now, before going into any numerical methods, how these numerical methods are actually developed. Okay, so let me tell you very briefly. Okay, like this is very famous problem. Okay, that Stefan problem, and Stefan actually solved this problem in 1890. Okay, 1890. So the thing is that means there is some solid material, there is a solid portion and some liquid portion of a material, and some solidification or melting is going on. And what he did, he wrote the energy equation for solid phase, he wrote the energy equation for liquid phase, and then he actually balanced the energy at the interface and he solved. Okay, the solution is very simple. If you assume the semi-infinite medium, the solution will be in this form. You can actually calculate the temperature distribution in liquid region, temperature distribution in solid region, and then the melt front movement you can calculate using this transcendental equation. Okay, so nowadays MATLAB or other types of softwares are available. You can easily code this, okay, to get the solution. Earlier days we need to do some iteration process to solve this type of transcendental equation. However, if I see this equation, what I can see is that I am getting liquid phase temperature as well as I am getting solid phase temperature, and I am explicitly calculating the melt front. Okay, in this case. Now, that means if I devise a numerical method or computational fluid dynamics model which needs to track the melt front explicitly, that means I need to move the mesh with that speed at which or with which this melting is occurring. Okay, and it is not very easy. Okay, means moving the mesh with the speed with which the melting is occurring, it is not very easy to calculate every time, and it will increase the computational cost. So now what are the remedies? Remedies could be fast. Remedies could be, okay, remedies could be, before this introduction, let me tell this. Remedies could be the fixed grid method, where I will not move my melt front explicitly Rather, I will track this melt front implicitly using my computational fluid dynamics model, and it will come under the fixed grid method. So that means I got two types of method actually, fixed grid method and moving grid method. So what I showed you through analytical model, it's a moving grid method. We use moving grid method very less, okay, but means widely popular method is fixed grid method, where computational cost is less. Okay, now if I say, okay, I will fix the grid and I will say use same methodology what the Stefan used, then I will not get the fixed grid method. So what I have to do, I have to modify my numerical methods. Now this is the first step to do this thing, where what we are doing, we are actually converting the energy equation, which is written in terms of temperature, into the enthalpy form. Okay, so enthalpy is basically C, specific heat into temperature. Okay, so CT, so that which is converted to H, and by right hand side is in the form of T. Now this is basically, you can solve analytically this model, but this is the starting point of understanding of any advanced model. Okay, where if you see that if I just non-dimensionalize it using these expressions, okay, you will see that you can easily get the you can easily solve this equation. Okay, let me tell you that solution here. So this is the non-dimensionalized equation, and I have used these non-dimensionalized terms to non-dimensionalize the equation. Now here, if you see the condition, whatever I need to solve this problem is that this Cp, when the temperature of the domain is same as the melting temperature, that means what? The theta will be 0. Okay, so that means during melting, theta I will set as 0. That is one condition. Okay, and phi, I will say that during that phase, I will say that phi will also we will carry some value. Okay, what is that value? I will let you know after this. Okay, first you understand that what are the main non-dimensionalized parameter we employ to non-dimensionalize this equation, and this I have converted to the enthalpy method. Okay, this is the first step in enthalpy method. So whatever we see in fluid or not in COMSOL thing I will cover later. So whatever we see which is enthalpy porosity method, this is the first step they actually adopt. Okay, where they actually replace, this is actually non-dimensionalized enthalpy, this is a non-dimensionalized temperature, and interface condition they will put using through this expression. So how to get, as I was telling, theta equal to 0, how we will get? Now let me tell, when it is in solid phase, the metal is in solid phase, you will always get H equal to Cp into T, means it's a sensible heat basically. Now when you will go into the interface condition, that means temperature is constant for pure material. Please remember this thing. Okay, and then only latent heat will come into picture. Okay, so that I have to model. I will little bit tell you later. Okay, let me go into the liquid phase. Now where means again sensible heat is coming, but the heat content here, it is the sensible heat of the solid phase plus the latent heat, because the melting has fully occurred. Okay, so that means my full energy content is now CPT in solid and latent heat in the liquid. Okay, so this is my liquid phase. So liquid phase and solid phase is not very difficult, whereas the interface, when I will get the interface where temperature is equal to Tm, what I need to do, that theta has to be set to 0 in this equation. Okay, and simultaneously I will get the solution of phi. Okay, basically I am trying to calculate the what is the latent heat content or what is the enthalpy content during that period. Okay, so obviously enthalpy will be CPT, which is the solid phase enthalpy, plus some portion of the latent heat according to the melt fraction of that medium. This is the idea basically. Okay, so now if I discretize that equation using my finite volume or finite difference method, I will get this expression. And as I told you that when the interface, when the melting will occur, I have to set this condition, and when solid will happen, then I have to set this equation. Okay, expression, and similarly during liquid I will get this expression. Okay, so using this expression you can actually do you can solve this problem for the one-dimensional case. Okay, this is the first step towards that. Now if I employ this method and try to calculate the same thing of that Stefan equation, what I will get is that this type of wavy profile. Okay, now how to arrest this type of wavy profile? And second point, another question is why this wavy profile is coming. So this wavy profile is coming because the space or the delta x distance or the grid spacing is very high. Okay, if you take very large delta x, then obviously you will get very visible wavy pattern in your simulation or the melt, say any temperature profile. Okay, so which should not be. Okay, I mean, see, you always expect that no waviness should come in the solution. Everything should be smooth. Now, what are the remedies? One remedy is that you have to reduce the grid spacing. One, that means you have to find the grid in your numerical model, or you can employ more advanced model. What that model? Okay, that model we called advanced enthalpy model. What Fluent or some softwares employ. Okay, here I am not adding porosity term because right now I am only going through the energy term. When I will include Navier-Stokes equation, you will see that porosity will come into picture. So very simple. Whatever I have derived, I have showed you analytically. That I have incorporate, means I have converted the energy term into the energy equation into the form of or in the form of the enthalpy, and then I impose this interface condition where I am implicitly actually calculating the male front. Now here one thing is that this term, if you just do this solution, means if you just divide the whole H, capital H means total enthalpy into the sensible enthalpy plus latent heat content during melting, okay, then you will get this expression, okay, in the energy equation, where this delta H you have to update, okay, at each iteration or each time step. Okay, that means latent heat content or fraction of enthalpy content at each time step during melting you have to update. So that means you need some other scheme to incorporate it. Okay, so now how Fluent or any software actually track this thing? Not the COMSOL. No, COMSOL adopts different methodology, which I will tell you later. Okay, so they actually say that, okay, if the melting is occurring between solid dust and liquid dust, and in case of pure material it will be T melt. Okay, so then you should take this value. Okay, so FL is the liquid fraction, LP is the total latent heat. But as I told you that when the melting starts, it doesn't have any, means latent heat should be zero, means FL is zero, basically liquid fraction is zero, and when full melting has occurred, then FL should be 1. That means you should get full latent heat, okay, or latent heat content. Okay, so that you have to remember. Okay, so now I have to devise delta H, or I have to calculate delta H updation scheme so that I can get this value at each step. Now understand one thing, this is del rho delta H by del T is a source term. If in numerical model the source term is there, that means you have to calculate explicitly at the beginning of any numerical scheme. So this is that update scheme, and which actually you get after discretizing this equation, which I am not going through it. It is given in any paper. Okay, so this type of updation scheme you will get. And if you numerically calculate the temperature at every location, you know the melting temperature. Then if you put some relaxation factor, which is in the form of lambda, like 0.4, 0.6, okay, and CP is the CP means this sensible heat basically. Okay, then you can actually update the enthalpy at each time step as well as each iterative step. Okay, and you have to solve this method iteratively. This is the main idea. Okay, and this is the profile for enthalpy versus temperature of any phase change. Okay, so during the phase change, latent heat will come into picture. Here it is only depicting. Now when we do model, first understand, we have to assume few things. Okay, here first my assumption is the flow is Newtonian. So that means whatever the governing equation I will tell you, it depends on the assumptions basically. First is fluid flow is Newtonian, then laminar, incompressible. Okay, local thermodynamic equilibrium exists. Otherwise, you will not able to assume many things like at interface. You will assume the solid temperature and the liquid temperature will be the same. Okay, if it is not, then it is different. Okay, so those things has to be, in order to assume that, or in order to take that, you have to assume this. Then we will assume at present that thermophysical properties of solid and liquid phase will remain same. But later on I will vary it. I will show you that model also. And also I will say that there is no shrinkage effect right now. Okay, my model is very simple. Now, if you see that this is the, now if this is my full-fledged equation where I am using continuity equation, momentum equation and energy equation. Now see these two terms, this SI and SH in momentum conservation equation and energy equation. Okay, now this momentum equation, this source term is basically tackles the melting front. Okay, whereas this SH, which I just show you, that minus del rho delta H by delta T, is that source term. Okay, which actually take care of the phase change. Okay, so now how I should model this? So del SH I have already shown you how to model. So there is no different thing. But how I should model SI? Okay, that source term, which will actually tackle the melt front during the solution of this momentum equation. So this is normally done by three methods, which is known as switch off method. Second is source term method. Third one is variable viscosity method. Okay, now what methods employ Fluent or any other software? Okay, depends. So first, that you need to understand, like when there is a solid to solid, a solid to liquid, means there is no phase change, say, then I will use the switch off method or variable viscosity method. Fluent normally employ variable viscosity method. Okay, where they set viscosity as very high value. Okay, if you see this equation, if you set viscosity very high value, then you will see this momentum equation will go to 0. So, but if you put the viscosity as finite value, this momentum equation and conservation equation will be finite. Okay, so it will not go to the 0 value. So that's why every Fluent or any software actually handles that. So variable viscosity method, I hope you understood. Now source term method, this is employed when there is a phase change from solid to liquid. Means from solid there is a velocity is 0, but in liquid phase velocity should be some finite value. Okay, so how to do it? Actually they model it, that melt front, they model it using the porous medium. Okay, or porosity. That's why it is called enthalpy porosity method. Now this porosity will come into picture. So they say that porous medium means if you pass fluid through that medium, there will be some pressure drop, as you know, using Darcy equation. Okay, so that is modeled using here, in this case, carbon-Kozenski equation. Okay, and we don't use Darcy model equation for modeling this A or this source term. Rather, we use some other different form of this Darcy equation, which is called carbon-Kozenski equation, which is very easy to employ because that equation actually correlates between the liquid fraction and the morphological constant. Now, if anybody has used Fluent for solving this, say, a solid to liquid, they will see that this value needs to be given. So this is that value. So normally, Fluent by default is giving 10 to the power 5, whereas normally it is given as 1.6 to 10 to the power 1.6 into 10 to the power 5 or 6 value we give. Okay, now I will show you what are the implications of this, but this is the background of that modeling approach. So what is the algorithm normally all software use? So first you initialize, if you want to write a code also, same methodology you have to follow. You have to initialize temperature and velocity. Then as it is an implicit based code, so you have to store the values at old variables and you have to use the Gauss-Seidel method or line by line TDMA method to solve it. okay, this is for not for the Fluent. Fluent use different solver part, which I don't know. Okay, but normally we employ some line by line TDMA or some Gauss-Seidel method to solve it. Okay. Now, as I told you, there is a good implication of this C, that morphological constant. People have seen that if you change the value of C, this profile also changes. That means if you plot melt fraction versus time, if you give less value of C, that melt will be happening very quickly. Melting will be happening very quickly. Whereas if you give the value of 10 to the power 5 or 1.6 into 10 to the power 5 or 6, you will get more or less good value which matches with the experiment. So obviously you have to have some experimental result to fix this morphological constant, which you need to give in any commercial software. Okay, especially in Fluent or finite volume method based software. Okay, this is the first step. Now, till now, whatever I told you are all based on the enthalpy porosity method, what Fluent employ. Now, what COMSOL employ is apparent heat capacity method. Okay, apparent heat capacity method is very easy. Okay, why? So what you have to do is that you have to modify the specific heat. Okay, obviously we know during solid and liquid there is specific heat, which is Cp. But during phase change, what they do, they use modified Cp, which is Cs plus or C, some value say specific heat plus dl by dt. Okay, so dl means latent heat divided by delta T. What is this delta T? The delta T is basically the difference between solidus and liquidus. So if anybody is using COMSOL, they will be asked to put this delta T. Okay, so that's why this is the difference. Okay, just one thing that you just please remind me at 3:30 because I don't have any watch with me. Okay, then I will speed up my thing. Okay. Okay, so this delta T you have to give. Now, the problem with apparent heat capacity method is that if it needs delta T, means temperature difference over which the melting occurs. But for pure material, you see there is no delta T because there is a fixed melting temperature. That means what it means, that you cannot use apparent heat capacity method convincingly for pure material. Be careful about this using this material methods. Okay, so then what? But people will argue that no, why not? I cannot use. Yes, when you can use that, means you can use if you calibrate or if you validate your model, or if you calibrate your model with experiments. Like I have given some delta T, for example 1 degree or maybe 0.01 degree, okay, and try to match that experimental result so that I can use this apparent heat capacity method. So that's why I'm saying convincingly, without doing any experiment, without doing any validation, you cannot do anything with these methods. Okay, be careful about that. Okay, so this is my this is my first note on this methods. Okay, now these are the two methods very widely applicable and people use very widely, and these are very popular methods. Now there are some other methods which called temperature transforming model. Basically this is also based on similar type of advanced apparent heat capacity method, but here they modify the term that CP0 or according to their definition using this expression. So if you really see, it's basically a short of the combination of apparent heat capacity method and the enthalpy method they employ in this case. Okay, this is a mixture and this is not very widely used, but still these are available. Okay, now when you do impure material, metal analysis, that means if, for example, right now I'm taking only example of paraffin. If I want to analyze this, okay. So in that case, paraffin, you don't know the composition of paraffin. Paraffin is actually a mixture of hydrocarbons. It's not a pure material. Okay, so paraffin is a mixture of hydrocarbons, but you don't know which hydrocarbons are there in what percentage. Okay, that's the problem. So that means if you don't know that percentage, you cannot employ the species equation. Okay, species equation which actually calculates the percentage of that component or that composition during the phase change basically. So if you don't have that species equation, that means you have to rely on the latent heat versus T solidus and T liquidus, liquidus temperature and solidus temperature. Okay, so modeling will be in that way. Okay, so that modeling is very simple, like that pure material only. This
Sorry to
will be the
interrupt, sir.
updation scheme.
It's around
Yes.
3:30.
Okay, I will little bit speed up. Okay, so the updation scheme will be different, where you have to incorporate T solidus and T liquidus in this way. Okay, so this is the way we actually employ the advanced enthalpy method for impure metal. Okay, now as I told you that if I have packed bed type of system, I can use the discrete element model, or another model I can also use, which we called porous medium model. Okay, now in porous medium model, what happens is that we actually consider these balls, okay, or these spherical balls as porous medium. So porous medium, what is the difference between discrete element model and porous medium model? In discrete element model, you are considering this material as distinct. Okay, you will be modeling the spherical balls. Okay, whereas in porous medium model, you don't actually model this. Okay, this capsules. Okay, rather you will imagine this capsule as porous medium. So in discrete element model, you will be getting microscopical analysis, whereas porous medium will give you macroscopic analysis. Okay, it's an average, short of average value. But in most of engineering situation, we are not very much worried about microscopic analysis. Okay, where in so many cases we want what is going in and what is coming out. Okay, inside what is going on, we don't need much. Okay, that's why this type of porous medium model is used. Okay, and also porous medium model is very easy to implement, and it is very less computationally expensive. That's why it is very widely, it is very popular. Okay, so now different modeling approaches are there, like single phase model, then concentric dispersion model, continuous solid phase model, and Schumann's model. Actually, Schumann's model was the first model, even this way he developed. Then this concentric dispersion model and this continuous variable model, these variants came. Okay, there is not much of a difference. I will show you one by one. Okay, what we do is that first we see the capsules and we first calculate the porosity, and we write the continuity, momentum, and the energy equation in terms of the porous medium model, or we add porosity. Okay, if you do some analysis, you will get this volume average continuity equation, volume average momentum equation, and energy equation. I will show in the next slide. You will get where the porosity will be involved. Okay, so and the source term, similar to that case, our earlier case, will be different here a little bit, where here the porous medium is actually the resisting the flow. Okay, so that modeling you have to do through permeability, which depends on again porosity, and for different structure. Now here for different structure, this permeability varies. Okay, you have to choose accordingly. Okay, so then this is the moment energy equations. Okay, now when I do energy equation, there are two types of energy equation I can employ. One is thermal equilibrium model, another is thermal non-equilibrium model. Where I will employ what? In thermal equilibrium model, actually Fluent offers both the models. Okay, now question is where you will adopt which one. So thermal equilibrium model you will employ in those cases where the solid particle thermal conductivity and the fluid thermal conductivity are not different much. Whereas if the solid particle thermal conductivity is, let's say for example, 1 order, 2 order, 3 order higher than the liquid thermal conductivity, then you have to use non-equilibrium model. So when you use equilibrium model, it is very easy because you are assuming everything as one single fictitious material and use the equilibrium energy equation. But when you employ non-equilibrium model, this is one example of that equilibrium model. I have simulated the metal that balls in this phase change material, and then I calculated the velocity distribution as well as temperature distribution in the domain. Okay, but when I use the non-equilibrium model, then that thing comes. There I have to employ two different types of equation for heat transfer fluid and the material. So again, here I'm saying material, I'm not very specifically saying phase change material, because this model is universal. Okay, it means phase change material means you have to incorporate the phase change source term extra, nothing else. Okay, but this I'm just talking from the broad perspective. Okay, so in energy, but how these two energy equation will be coupled? This energy equation will be coupled to this source term. Now, if anybody has used this say module, he will be asked to give what is the interfacial heat transfer coefficient, and Fluent has certain definitions. Okay, like how they unit wise. Okay, so that unit you have to convert basically. Okay, and you have to give this value. So I have given some expression for this calculating this HSF, means interfacial heat transfer coefficient, as well as how we'll calculate the interfacial or specific surface area, that is basically 1 by meter. Okay, so I've given some expression, but normally these are employed or they write the thermal equation or temperature equation differently, and this is coupled to this expression, which is the input to your model. Okay, and then in concentric cylinder model, similar approach will be there. Only if you see the difference between STF, these are both are same, except where you see in one case means in concentric dispersion model, means variation in the heat transfer fluid is, or PCM also is only taken in height, whereas in continuous solid phase model, variation is also taken in art direction. Okay, but question is then means continuous solid model phase model is giving me good results. No, means it is giving me two-dimensional feature. Why I will use concentric dispersion model? No, concentric dispersion model has one big advantage, is that you can individually calculate the temperature distribution inside this spherical capsule, which is not possible in this case. So you have to wait that the model, that which one you will use for your situation. Okay, then only you can select the proper case, proper model. Okay, now one simple this model we have developed in our ANSYS Fluent. So this actually we developed 5 years back. Okay, when Fluent was not this model. Even today also they have not don't have this module. So we have used this UDF, whatever the equation I showed you. No, we have used UDF and UDS there to code the source term, and then we actually try to validate with our own experiment result, and we see that okay, fairly it is matching. Okay, still why it is not matching fully, I am telling you, because in our model we assume that phase change material is undergoing phase change from solid to liquid. That means I need to also solve Navier-Stokes equation. But very frankly speaking, we don't solve Navier-Stokes equation because Fluent does not allow you to solve one more Navier-Stokes equation. Okay, it has only one inbuilt Navier-Stokes equation, but it allows you to solve another means scalar equation like energy equation or species equation. Okay, so that's why we assume phase change material will remain solid, although it changes phase from solid to liquid, means I am not solving any Navier-Stokes equation basically. Okay, so that's why there is a deviation. So that's why when I told you that why deviations are coming from my model. Okay, now this model I can also employ for metal foam type of applications or metal matrix. Here we have employed metal matrix, but metal foam will also be same, only the difference will be in the permeability expression, as I told you. So you have to find the permeability expression for metal foam. So I will now I can use this metal matrix in the circular form or in the square form. Accordingly my source term variation will be there. Okay, so my source term expression will be different, and which I have to put in my model to find the expression. So this we have developed to validate our numerical model with whatever we are developing using say Fluent. Mostly we develop nowadays using Fluent or OpenFOAM. So we have to validate our model. So we have developed this, and then we see that fairly it is giving me results. Okay, again I told you why deviations are there, because I don't model the phase change behavior using Navier-Stokes equation. If I am able to do it, it should be coming actually. But again, there will be restriction because of the comments from the Fluent side. If I able to write my own code, then it is okay. I have to solve. I have to write one more Navier-Stokes equation basically for this case. Okay, now till now I haven't gone through any types of shrinkage. Okay, there is no volume expansion or volume contraction. Now if you incorporate that the shrinkage effect, this is now most advanced model. Okay, I hope it will come in near future in any software. Okay, that we can now do a shrinkage analysis using this model, where I will tell you the equations we will actually write in the same form of the earlier equations. Only the extra term, whatever we will get using different density, specific heat or thermal conductivity, that we will put into source term basically. So I can still use the Fluent code, or I can still use the console, or even I can still use the OpenFOAM. I have to use some extra source term basically here. Okay, so what are the source term? These are the, say for example, for energy equation, this is the source term because of the uses of different CP basically. Okay, for momentum equation there will be some extra source term also. Okay, which I haven't mentioned here. Mainly I have shown you that what are the extra source term it will come into the energy equation. Okay, now I have taken some cases where I showed that okay, when this is validated with the experiments, we have showed that our model is now predicting well with the experiments for 3 different cases. Means in one case I have chosen different rho s rho l, K scale will be different, CPS CPL also different. Okay, in one case this is melting with volumetric expansion, this is solidification with volumetric expansion. Okay, this case where also we see this is our experimental results. Means we didn't do, we have developed the model, we have validated it with that experimental result. Okay, we see fairly good matching with that experimental result using shrinkage. Okay, and in another case this is verification. I should not tell the validation. This is verified with one numerical model. They have also developed for a specific case where only they took rho s equal to rho l, means density difference. Okay, so that also matches very well. The interface model we match very well in our case. Okay, so this is actually done in OpenFOAM. Now I have briefly showed you the main modeling technique in the in a latent heat storage. Now I will go into the thermochemical storage, where we will be using the equation heat of reaction. Okay, or the conversion of from hydration state to the dehydration state. That type of equations or chemical reactions we will use. Okay, so principle of thermochemical storage is that you will be having some type of reactions. So endothermic, exothermic, which we know in our say 6th or 7th standard chemistry book, and we know what will be the heat generation. That will be our motivation to store energy. But here understand, whatever the thing we will do, we have to put in our code. Okay, so this is not done in Fluent. So this is done in console. Actually we have incorporated this in console. Some motivation why I should use thermal chemical storage, because it has very high energy density. So as a result you need very small material. Okay, but as you know that you need very small material, that means process is complicated, modeling is complicated, and the container containing of this material is also complicated. Okay, you will get good results, but everything means everything will be complicated now. All okay. So now there are various flows, means as this is a chemical reaction, we need to use some reactors. So so this type of reactors could be operated in closed mode or in open mode. Open mode means it is that reactor is open to atmosphere. In another case, reactor is in a closed loop, basically, simply. So here, as we are using hydration and dehydration, we need some type of chamber where we can store the moisture. Okay, this is the idea. Okay, now this is the open mode where we actually reject that moisture to the ambient. Now here some examples of thermochemical energy storage, like means strontium bromide, CaCO3, CaO, means not only hydration dehydration, we also take care, we also use carbonate type of application, chlorinate type of application, where the endothermic and exothermic reactions are there. Okay, now some typical examples of the salt hydrates and their energy densities. Now coming to the numerical model, where we are trying to model this 2D reactive bed. Okay, so understand that in this bed we have incorporated that salt. Okay, you can think of that's a molten salt, but it's not like a that type of salt. It's a basically hydrated salt. Okay, strontium bromide with 6 H2O. Okay, means it has 6 H2O in its molecule. Okay, so now our assumption obviously is we are not making very complicated model, like local thermodynamic equilibrium exists, moist air consists of water vapor and dry air. This we know from our thermodynamics. Okay, so here thermodynamics both as well as heat transfer will play a major role in developing the model. Okay, so all the assumption what you make in analyzing your moist air system here will also assume, but here we will write the governing equation in different way. So what we are again considering is that the material is packed inside this container. Okay, it's again porous medium. Okay, so that's why we write Darcy equation. So there are two versions of this equation. In COMSOL, Darcy equation you can write, or Brigham equation also you can write. But here we have used Darcy equation and we assume laminar flow. Okay, that's why. Okay, another thing that we write the species conservation equation for moist air. Okay, so and species conservation equation for water vapor, that how much is going out. Okay, and then we write the energy conservation equation. I will come one by one. Let me bulk first tell you the energy conservation equation of our full system. Then we incorporate the reaction kinetics, that how reaction is going on, how the reaction front is going on. If you see, reaction front depends on the partial pressure. Okay, this is coming from our thermodynamics knowledge. Okay, where we know that fugacity, all this thing. Okay, so now this is one dimension or first order reaction we have written. We can also employ second order, means more complicated equation we can write with this. Okay, and how we define the value of alpha, it's a number of molecules or number of moles of one material divided by number of moles of another material, and using the Clausius-Capiron equation we can calculate the partial pressure of that, because what happens that when we use this formula, where the phase change is occurring, because moist air is going out from this salt basically. Okay, so temperature will remain same, pressure will be little bit different, so we want to calculate that. Okay, so and the some source term how we calculate. Now Darcy equation, as I told you, it is a very simple equation we have employed, and the species equation mainly consists of the transient term and the advective term and source term, which is basically depends on your reaction. Okay, so how much moist air is depleted from the container, that I am trying to depict from here basically. So this is the energy conservation species conservation equation. If I follow the same logic, I will able to write the water vapor equation also. And boundary condition, here side walls are insulated. air inlet and air outlet. It's a two-dimensional analysis. Okay, and then we actually try to verify validate this model with some experiment. We haven't done any experiment on this, but recently we have started. But the thing is, we have seen, if you see, we have seen in one experiment our model predicts well with the experiments. Okay. However, in another case where we are seeing the temperature distribution, this is the global reaction advancement, in the sense how the reaction front moves, which is actually validated well. But when we come to the temperature, outlet temperature specifically air outlet temperature, we see that actually our model or no models are near that actual experiments. Actual experiment does not show. You see, this is the actual experiment. I hope you can see my laser pointer. Okay, so laser experiment does not go down. Okay, whereas numerical models goes down. So there are many issues with our numerical model which we need to develop further, like agglomeration is there, which we cannot take care of in our experiments, in our numerical model. So those has to be incorporated, but we need to know how to incorporate in consoles. Okay, so those are the things we still need to do. So summary is that several models we have developed, but still there are many ways you can improve your model. So that means you have to understand the physics, you have to understand the applications, then only you can incorporate different models, and then you will get the results basically. Okay, so I end my presentation. Please let me know and whatever the thing you want to ask me, I can able to explain those things. Please.
Have any questions, so you can ask.
Okay, if nobody is asking me any question, let me little bit tell you how we model that two-phase flow in heat exchanger, which is also a system, a thermal energy system. Two-phase flow means from liquid to solid, liquid to vapor. So there, this kind of modeling approach will not be useful. Okay, there what we use, that volume of fluid method mainly. Okay, where we try to figure out that from one phase to another phase, how much liquid or how much volume fraction has changed. Okay, from solid liquid to vapor first, and then using this volume of fluid method, we actually track the track the interface of that liquid and vapor. Okay. So there is one more method which is called level set method, okay, which actually employ for the even for the melting problem also, but also for the solid liquid to vapor problem. So what is now distinction between volume of fluid method and the level set method? In volume of fluid method, we use those applications, or we employ in those applications where free surface is there. Okay, like water is pouring in a bucket. Okay, say for example, where free surface is available. So there we employ volume of fluid method. Whereas level set method we actually use in those cases where there is no free surface, like in casting.
But sir, is there any method in solar energy where the liquid to vapor application is used?
From for liquid, yes.
Yeah.
So normally means, see, in solar if you see that even waste heat recovery, whatever, that you are converting water, means water from water to steam, no? So that's a two-phase flow.
No,
So
I'm talking about that. I'm talking about that heat storage. Like paraffin wax is used as a PCM.
We use,
But
it means,
similar kind of similar kind of liquid to vapor and vapor to liquid. Is it
No, no,
occurring
no.
in any solar?
No, no, no,
I
no,
think
no, no,
no.
no. Even not in any
Not.
case we use. No, no, no. You are
Yeah.
correct. There is a
Yes.
basically containment issue. Okay.
Okay. Yes. Okay.
But as a heat transfer fluid, water to steam, we mean, you know that we always use.
Correct. Correct.
But not as a storage. Yes, storage
not
we
as a
use. Yes, storage we use. Let me tell you, as a sensible heat storage. You know this solar drum or some what is called the principle based on which this our pressure cooker works. Okay, which is called, we call solar drum. Another name is there. Okay, so that we use. Okay, before the turbine. But the problem with that, the solar drum or all this thing, is that you will get the saturated liquid at the outlet. Although pressure is high, saturated liquid you will get, saturated vapor you will get. Now, if you get saturated vapor, no, the turbine blade will corrode. So that's why you need extra heating arrangement before the turbine.
Okay.
Okay, so that those are problems will come. I believe I have mentioned this thing. Maybe I didn't. Just 1 minute. Yes, if you have any other question, please let me know. But I just check this. Yeah, this one. This is called steam accumulator. Okay.
Yeah.
So this
Very
is
exhaustively you have discussed. Very exhaustively you have discussed all numerical methods also and with a specific applications. Really nice lecture.
Thank you.
Sir. Yeah, Bhaumik.
Yes, sir. Okay, sir. Thank you so much for the insightful session with the number of case studies. Actually, your session was really engaging and it will be very helpful to participants to understand the application of CFD for thermal energy storage system. Thank you so much for sir for accepting our invitation also on behalf of ADIT Institute of Technology, sir.
Thank you.
Thank you, sir.
Thank you.
So if you have any question to participate, you can send me mail. Okay, I can clarify also.
Yeah.
Sure.
Thank you.
Okay, sir.
Thank you. Thank you very much.
Okay, thank you, sir.
So I am disconnecting the call.
Yes, sir. Yes, sir. Okay.
Thank you.
Thank you, sir. Dear participants, the valedictory function will start at 4 o'clock. So, dear participants, I Bombay said welcome you on behalf of ADIT for valedictory function of AICT AQIS sponsored short-term training program on applied computational fluid dynamics for renewable energy and hydraulic machine sector. So I request to Principal ADIT, Dr. Vishal and Singh sir to address.
Greetings to all the participants. I hope all of you must have listened to different expert speakers from the renowned institutions across the country and gained insight into computational fluid dynamics with a special focus on different focus areas. This is a unique module that is being transferred from ADIT to engineering community for gaining an in-depth analysis, understanding of this particular domain. I hope you must all have enjoyed your sessions. If you have any doubts, please let us know. We will try to resolve them from you. And in time to come, in next month, starting from 1st of March, we are having another AICT sponsored STTP on CFD with a different thematic area. With this, I wish you all the best, and I hope you would use the knowledge gain for the development of the society and the students at large. Thank you, all the very best.
Thank you very much, sir. I request Dr. IDS, Head of the Department, to address.
Good afternoon to all. The department always invites good expertise, prominent expertise from the entire pan-India through the interactive sessions. All of you have taken the knowledge from all the IITs, NITs, then BITS Pilanis, then Tripura University, as well as industries like CAD FEM, then Metal Power Analytics. In this STTP, related to the computational fluid dynamics, means major thematic areas are wind turbine, wind farm, solar drying technology, centrifugal pump, cyclone separator, and bioreactors. Almost 144 different participants have taken active interest and interactions during this STTP. The participants are from the various cities like Chennai, Bombay, Nagpur, Delhi, Vadodara, Ahmedabad, Pune, Surat, and Kanpur. I wish that whatever you have learned, that you will try to utilize at your organizations and try to impart them among the students or maybe to the PhD scholars. And whenever you will find a time, you may also visit the Mechanical Engineering Department of A.D. Patel Institute of Technology. We may have a fruitful interactions further in this domain also. So I once again thank you everyone, and I am also thankful to all the prominent experts. With a short notice, they are ready to deliver their expert talks on this thematic area. So thank you all once again.
Thank you very much, sir. Now I request Dr. M.I. Saha, sir, Professor Mechanical Engineering Department, to address.
Very good afternoon to all participants, respected principal sir and head of the department. It's really a matter of pleasure for us to finish this program successfully. It is always difficult to search speaker in a specialized thematic areas. And for that thing, I congratulate Professor Baumik said for taking lot of pain and finding the speakers from the Pan India. Many speakers were contacted, many of them regretted, and then we reach up to this level. Because very specific area, always difficult to find speaker, and ultimately we did this. And as our principal sir said, the one more phase of same type of workshop is coming, but different thematic area, which will be starting from the 1st March 2021 to 5th March 2021. And there also we have targeted many good speakers, many of them already confirmed. I hope that you will join again in that workshops also. Thank you for sparing your valuable time and learning about the computational fluid dynamics in renewable energy and the hydraulic machine side. Once again, thank you. Thank you very much.
Thank you so much, sir. Now participant may share their experience about the program. If anyone want to share experience, then okay. So there is one message in chat box. Thank you, Mr. Mahesh Kataria, for the appreciation. So I am Baumik Seth, assistant professor and co-coordinator for this STTP on applied computational fluid dynamics during 1st February to 5th February. To show my gratitude to the Almighty, then I would like to thank AICTE for sponsoring under AQIS. I would like to thank Sri Engineer Bhikhubai Patel sir, President CVM University. Along with him, I would like to thank Sri Manishbhai Patel sir, Vice President CVM University, Dr. S.D. Patel sir, Honorable Secretary CVM, and Dr. P.M. Udani sir, Director General CVM University for that support. I would like to thank Principal ADIT, Dr. Vishal Singh sir, who is also the coordinator of the STTP, for giving me this opportunity. Thank you, sir. I thank Dr. Y.D. Patel sir, head of the department, and Dr. Mitesh Saha sir for giving his support. After this, I would like to thank all the experts for various IITs and other reputed institutes and university for accepting our invitation and delivering that talk. I would like to thank all the participants to join the session throughout the duration of the STD. At last, I would like to thank all the fellow faculty members of Mechanical Engineering Department ADIT for their support. I would like to thank each and everyone who have helped me directly or indirectly for this duration. So thank you, everyone. Participants are requested to fill feedback form in the link provided in the chat section, followed by the link of quiz. Thank you, everyone.